So for this afternoon class, we're going to talk about the work in pumping a fluid out of the top of a tank. Now, this is another useful example of the application of integration, and this is concerning computing work that comes in pumping of fluids. Now, this is often illustrated in the context of we'd like to empty a storage tank by pumping the fluid out the top of the tank. So the fluid is to be pumped up out of the tank. Now, this situation is different than our previous examples where the forces involved are constant. Now, after all, the force required to move 1 cubic foot of water, and that is about 62.4 pounds in mass, is the same regardless of its location in the tank. Now, what is variable in this case is the distance that cubic foot of water has to travel. Now, water closer to the top of the tank travels less distance than water at the bottom, thereby requiring or producing less work. So in this case, our force class is constant because the amount of water that is to be pumped out of the tank, if we talk of a particular element, is the same. It is this time the distance that this particular element of water or volume of water, the distance that it covers as it is being pumped on top of the tank, that is changing. So let's look on 3 examples concerning this kind of work, and we'll start, of course, with the simple one. Now here in example 5, you could see a cylindrical tank. Okay, this is your cylindrical tank. Let me just use it. So this is your, cannot be seen, so just use the arrow. So this is our cylindrical tank. So a cylindrical storage tank with a radius of 10 feet. So this is the radius of our cylindrical tank, and a height of 30 feet. So this is the height of our tank, is filled with water which weighs approximately 62.4 pounds per cubic feet. This is actually the mass per unit volume or the density of water. Compute the amount of work performed by pumping the water up to a point 5 feet above the top of the tank. So if we have a 30 feet tank, okay, this is how tall our tank is. The water inside the tank will be pumped out of it 5 feet above our tank. So this time, the total distance that will be traveled by water as it being pumped out from this particular cylindrical tank is 35. Because the height of the tank is 30, and then you will have to add 5 to that because it would be 5 feet above the top of the tank as to the, shall I say, the elevation in which the water is to be pumped out of the tank. Now, please refer to the figure here on the right side for our illustration. And this is the differential volume of water that is going to be pumped out of the tank 5 feet above its top, on its top. So you have now this particular distance. If this is y from the bottom of the tank up to this point, then for this volumetric, or shall I say differential volume of element of your water, it will have to travel 35 minus y. Okay, because this yi specifically, if this particular differential element volume that is of water is y sub I distance from the bottom of the tank. So you're going to subtract that from the total distance of 35, then that would be the distance covered by this differential volume of water inside your tank. Now, consider the work W sub I of pumping only the water residing in a particular interval. In this case, that interval is the ith interval, as you can see in the figure. The force required to move this water is equal to its weight, which we calculate as the volume, That is why you have here the differential volume. So the volume times the density will give you the mass. If you're going to multiply it with the gravitational constant, then that should give you already the weight of the water. Whatever is the weight of that particular differential volume of water will be the same amount of force that you need. That way, that particular differential volume of water can be pumped out of the tank. So the volume of water in the subinterval is, let's say, represented by V sub I is equal to, this 10 squared is the R. Okay, let me annotate. So in terms of volume, I'll place it here. We have the area times the, I'd like to represent the thickness of the differential volume as dy. You can see it in here as delta yi. So the area in particular is the area of this circular face. So what is the area of a circle? So that would be pi r squared, and you have dy. So that is why you could see here a 10 squared pi, because our radius is 10. So 10 squared pi times dy, the differential height of this differential volume of water. So in here, it's represented as delta y sub I. Okay, I just typed it for the second time around here. It's the same thing. Its density is 62.46. So, now double siya class. So, it should be here only. 62.4 pound per cubic feet. Okay, so that's the density. So, the density, so we'll have mass over volume is equal to the density. So if you're going to cross multiply the volume and the density, you'll have the mass, which is equivalent in this case to the force that is needed to lift this differential volume of water to the height that is indicated. So in terms of mass, you will have now the density times the V, and this is the V. So if this V, which is 10 squared, which is 100 pi, if you're going to multiply it with 62.4, you will have now 6,240 pi delta yi pounds. So this one is another double pasting in here. So omit this one as well. And this, okay? Na double lang siya. Okay, the water will be pumped to a 0.5 feet above the top of the tank, that is to the height of y equal to 35 feet. Thus, in terms of the distance, this particular differential volume of water that is going to travel, that would be 35 minus yi, because that yi is actually the distance of this differential volume of water from the bottom of the tank. So if this is y sub I, then this must be 35 minus y sub I. So the work that we are computing is still equally based on the formula. So work is equal to the force times the displacement. Okay? Work is equal to the force times the displacement. The displacement is the same in direction as to the force applied. So you can see in here that your volume is this one, 10 squared pi delta yi or dy, and that will be equivalent to a force after multiplying it with density of 6,240 pi delta yi. Now you could see that in here, your 6,240 pi dy. So this two, it was only written here in this manner, is actually the force. That's the force. The displacement is the distance in which this volume, differential volume of water is going to travel as it is being pumped out of the tank. And that distance is 35 minus y. Now, as to the limit, so this is your displacement, and these two is your force that makes it work. Okay, now your limits of integration is 0 to 30. Why? Because your tank is only filled with water to the same height as of the tank. So you cannot have water higher than the height of the tank itself. So that is why your limit of integration here for the lower limit is 0 and the upper limit is 30. You don't place here 35 because your water inside the tank, your Y here, the height of the water inside the tank is just under 30. It's not 35. It is the distance that is being traveled by the differential volume of water that reaches up to 35. So take note, this is the common mistake of my students before, that instead of writing the limit 0 to 30, they will write 0 to 35. No. The Y here in the first place represents the, how shall I say, the location of that particular differential volume of water, kung diin man na siya, nga YI. So, hindi man siya magsubra sa 30 because your tank is only 30 feet in height. So, if you do the mathematics here, it's just a simple case of power rule. You have this one. So, in terms of the amount of work in emptying, so meaning all of the water inside the tank will be pumped out of it. So, 5 feet above the tank. So, the total work expended for that is 11,762,123 foot-pounds. So, in here, this on the premise that, again, your G and your G sub C here are equal. Okay, they are equal because if they're not equal, then this pound mass here, which is 62.4, will not be the same equivalent weight in pound force if your G and your G sub C are not the same. Your G is the gravitational constant in that particular location where this tank is located. So the G in Bacolod, for example, is different than the G in Canada, whatever city in Canada we're referring to, or something like that. So the G is different, but the G sub C is the conversion factor in converting pound mass feet per second square to pound force. Okay, just a little review on your physics. So this is the work done in pumping all of the fluid out of the tank to a height of 5 feet above the top part of the tank. So it's the tank now is emptied in this case. Any question? Okay, so there are no questions. Okay, I clear my markings. Then we'll proceed to the next. So this is a case class wherein our cross-sectional area is fixed because we have a cylinder. So what is varying in this case is just the height or the displacement of the differential volume of water from a particular location. So the displacement is different if we base it on a different subinterval or level of your differential volume of water. Now let me go to another sample problem, but this time we'll have a different shape. So we have here a conical water tank. It's in the shape of a cone and has its top at the ground level. So this is ground level. So that's ground level. Now, let me continue. And its base is 10 feet below the ground. So if we have the top portion of this conical tank, storage tank, as ground level set as 0 Y, then 10 feet below the ground is the base of this particular conical tank. So we place it at -10 in terms of its Y coordinate or ordinate. So it's -10 because it's 10 feet below the ground and ground is set at 0 feet. Now, the radius of the cone at ground level is 2 feet. So you can see this is the radius. It is 2 feet. It is filled with water weighing, so the same density of water in the previous sample problem, so 62.4 pound mass per cubic feet, and is to be emptied by pumping the water to a spigot 3 feet above the ground level. So you are to pump water at this portion here. So 3 feet above ground level or above the top of the tank. Find the total work performed in, take note, emptying the tank again. Okay, just a minute, class. So for this problem, our solution will start with identifying the very important coordinates that will represent later on the relationship between the changing radius of this differential volume of water that needs to be pumped out to 3 feet above the ground. Okay, that is also the top of this conical storage tank. In this case, class, it's not similar to the previous problem wherein the radius is fixed. This one, it's varying depending on the y. So later, we will set an equation relating, or we'll make an equation relating this radius, let's say x, with respect to y, which is the displacement of this differential volume of water that we need to pump out of the tank. Okay? Now, so let y equal to 0 represent the ground level, and hence your y equal to negative 10 represents the bottom of the tank. So this was already mentioned. So you have negative 10 for the bottom of this conical tank and 0 for the top of the tank, which is right on the ground. Now, the figure shows an element, a cross-section, which is a circle. Now, the radius of this circle is varying, as I have mentioned, and it depends on the y. So as you could see, when your y is equal to negative in here, there's no radius because this is the tip of your cone already. So it says here that when your y is equal to negative 10, the circle has a radius of 0. When y is equal to 0, right on here, on the top of the tank, on the ground, your radius is equal to 2. And as such, in this case, we have now these 2 points, which represents, of course, the coordinates x and y. Negative 10, 0 for this point here. This is your negative 10, 0. And, or shall we say, in terms of x and y, if you're going to represent it in terms of x and y, that would be 0, negative 10. Okay, and this one is since it's written here in terms of y and x, so you have here 0y and your x is equal to 2. So these are your 2 sets of points. Now allow us to find the equation of the line that gives the radius of the cross-section circle. Meaning, we will determine the equation of this radius. This radius will be represented by x in terms of y. So where do we get that particular equation? We get it on these 2 sets of coordinates. Now, how do we find that? So in terms of the equation of the line, you have y equal to mx plus b. Now, the first thing that you are dictated to do when you find the equation of the line is you determine the m. So in this case, you could see in here the r in terms of y. So this r actually is x in here in our orientation because it's horizontal. As a function of y is equal to 1/5 y plus 2. Now you may wonder, how did this particular 1/5 y came about? The slope, which is 1/5 y. Now, you could see here in our set of coordinates that this is your y and this is your x. So, 2 minus 0. So, in this case, you have 2 minus 0 divided by. So, you started with this point. So, you will use its x first. So, 0 minus 10. So, you have 0 plus 10. It's supposed to be minus 10. In that case, it will give you now 1/5. Okay? This 1/5 and this x, which is your y, plus. Now, how did this b came about? Simple. You just assign values based on the points that you have in here. So when you can see here that your x is 0, so this is your x here, you set this to 0. 0 is equal to 1/5. What is your y? Your y is, okay, your x is, sorry. Your x is 2. So, li na siya galing class. Kaya ang orientation is una ang y, dayon ng x. So, your x is 2. So, I'll change this. Your x is 2 and your y is 0. Just like in here, your radius is 2, your y is 0. So when you substitute it in here, you will have a b which is equal to 2. And that's the b that you're going to place in here. Now you will have an equation relating the radius in terms of y. And that is 1/5 y plus 2. This radius is actually the x that we have in here. The 2 that we have in here. The way we write the 2 points in here is instead of starting with x followed by y, this one starts with y followed by x. Okay? So these points that you have here is written like y, comma, x. You can have it interchanged, but you will still have the same, of course, the same answer if you just substitute. So this x actually, or rather this r of y, or r as a function of y, is your x. Now, the purpose again of these 2 points is for you to have an equation for that changing radius. Your radius here is changing, and it should be expressed in terms of that displacement, which is y. The radius is a function of the y. So that is why, since it is the x which is the function of the y, it's written here, sulit siya ang pagsulat instead of writing it x followed by y. In here we write y followed by x because in this case it is the x that is dependent on the y, not the usual case wherein it's the y which is dependent on x. Now this is the radius of this differential volume of water that is to be pumped out of the tank. Radius alone. Since it's the radius and this is also circular, then in terms of the cross-sectional area of the circular portion of your differential volume of water, that would still be pi r squared. So the volume that you could see here, the volume equation in terms of y is equal to pi r squared now is 1/5 y plus 2. Then this is your thickness, the dy. Pi r squared is the area and the thickness of this differential volume is the dy. A very small height of the differential element. Specifically, a very small height of the differential volume of water that needs to be pumped out of the tank. Now, this is the volume. So, we need the force again. So, just like the first sample problem, volume has to be multiplied to the density. So, you could see here that we have the density times the volume being equal to the force, which is a function of that displacement. So, meaning the force that is needed to pump the water out of the conical tank to a height 3 feet above the ground is a function of the level of water inside the tank. So it's a function of y. So the force is changing, a function of y. Now this is your force already. Now in work, we need the displacement. And what is that displacement? The same principle that was used in the first sample problem. If this is the level of this particular differential volume of elements, so it's of level negative y from the bottom of the tank or from the ground. So this is negative 10 and this is, let's say, y at this particular level. So the displacement then can be represented as, or the distance that will be traveled by this differential volume of water will be, you have here 3 and 10. So you have to get the total distance covered. That would be 13. So 3 minus 10, that would be 13 minus y. And as such, you can see that the distance covered is, that you have here 3 minus y for the height. 3 minus y because this entire thing here is 3 from in here. Now, it is the height of the water inside the conical tank that will be -10 to 0. But in terms of that displacement, I stand corrected. If this is y, so it should be, this is 3 based on our representation of 0, y here on the ground. So this is 3 minus y. This is your, so this is your force together, So this is your force together with the dy now. Okay, that's your dy, the thickness of the differential volume. This is the density. This is the pi r squared dy. So all of this is your force. And this is your displacement. Take note that the displacement is again based on the orientation that we have set, wherein the top of the tank is 0 in y. So then the total distance is just 3 because this is 0. So 3 minus y is the total distance that will be traveled, or the distance in which this particular differential volume of water will be displaced from this point up to this height here above the ground. So 3 minus y. Now, it's different than the limits that you have used in here, because the limits that you have used in here is based on the water, the height of the water inside the conical tank. Not the displacement height, but the height of the water inside the conical tank. So it is from -10, again, based on our orientation, to 0. So you have here -10 to 0. The rest is just mathematics again, because after here, if you do expansion, you just square this one and then multiply it by 3 minus y. By power rule, this will be the corresponding expression that you will arrive at. And then just use, by the way, by expansion, expanding this one, this is the expression that you will have. You need still to perform power rule on this expression and substitute the limits -10 to 0. So the total work in pumping the water inside this conical vessel or tank is 14,376 foot-pound force. So it's understood to be pound force. The key in solving this problem, class, is in setting up these 2 points. And next is in making an equation relating the radius, which is x, to the y, the height of the water inside the tank. So at any particular height, this radius changes, because at this part here, for example, the radius here, of course, is bigger than the radius in here, which is smaller. So nag-change ang radius based on the height of the water inside the tank. So that particular relationship between radius, which is x, as a function of y is this. Radius as a function of y. The rest is just, of course, just substitution to the formula for the work. Any question? No question? So everybody gets the process of setting up this equation relating the radius x to y, which is the height of the water inside the tub. No question with this, because this is just the part for me that is quite challenging. The rest is just, of course, making sure that this radius is used in finding the volume, the differential volume of this differential element. So no questions? Sige. We'll go to the last one. So I think I have example number 7 here. This is a swimming pool of different cross-sections. So a rectangular, sorry class, let me just. A rectangular swimming pool, so meaning class, if this is drawn, this is just but the cross-section of your pool. So if it's drawn, it's like this. Okay, I'll just extend the drawing so you can visualize. So this is the cross-section of the pool. Okay. It has a rectangular cross-section, but on the sides, this would be the cross-section that you will be able to see. So a rectangular swimming pool is 20 feet wide. So this is the 20 feet. From this part here to this part here is 20 feet. Okay? It's 20 feet and has a 3 feet shallow end. So this is the shallow end. And a 6 feet deep end. So this is the deep end, okay, for the pool. Now it is to have its water pumped out to a point 2 feet above the current top of the water. So the current top of the water, if this is our swimming pool and it's full of water, so it's 6 feet. Water is to be pumped out 2 feet above this particular level of water. And you could see that this particular cross-section on the side of our rectangular pool is now written here in the Cartesian plane. And you could see that this is the top of the pool filled with water, and this is the point above where your water needs to be pumped out. So the pool will be emptied and the water is to be pumped up out to a height of 2 feet above it. Okay, the cross-sectional dimensions of the water in the pool are given below. So note the dimensions are for the water, not the pool itself. So compute the amount of work performed in draining the pool. So the cross-section that is drawn is that of the water and not the pool itself. So that's the dimension of water. Okay, you have here 20 feet by 25, 20 by 25 feet rectangular swimming pool, and this is its cross-section on the side. So kids will swim in this portion while adults will swim in this portion because it's already the deep end. Now, for the purpose of this problem, we choose to set y equal to 0 to represent the bottom of the pool. So this is the bottom of the pool, and the y there is 0, meaning the top of the water is at 6 feet. So if the pool again is full of water, so the top of the water is 6 feet. And this particular pool water will be pumped out to this height, 2 feet above the top of the pool. The figure shows the pool oriented with the y-axis along with 2 differential elements, as the pool must be split into 2 different regions. Now in here, the cross-section of the side of our rectangular pool will be divided into 2 different regions. I'd like to show the division part. So this is how it's going to be divided. So I'll just use na lang the red. So when you solve this problem, you will have 2 integrals that you will just add afterwards. So your first region or your first portion is this one. So you have this rectangle. Okay? And if I will draw again like that so you can visualize, easily visualize. Sorry. Okay, that's it. So this is your first portion. Okay, that's out your first region. The next region is the one in here below. So may-ari na isa dalawa. Now, the cross-section of this region is not a rectangle. So in this cross-section here, you have a rectangle, but in here, you have a trapezoid. Okay, so you will find first the work in pumping out this, the water in this upper region. Then determine the work also in pumping out the water at the lower region. Okay, and we just erase the markings here so it will not hamper our computation. Okay, wait lang. So this is our pool. Okay, so you have that. Now you have two different regions for our pool. Now let's say we will first determine the work done in pumping the water on the top part of the pool, which is actually a rectangular parallelepiped, as it is referred to in solid mensuration. Okay, so let me see. Let me just clear my marking. So that's it. You can take a picture if you want. Now we go to the next slide. So the top region lies on the y interval 3 to 6. So what it meant here is that our top region will be using this interval 3 to 6. And our lower region will be using the interval 0 to 3. It's as such, there's a cut in here. Okay. Now, where the length of the differential element is 25, so this is still 25 class. This one is 25, and in here you have 20. Okay, we'll just not draw it through and through. As the pool is 20 feet wide, so I have placed it here already, the length is 25. The differential element represents as a slice of this water is having a volume of 20. So this rectangular face, 20 times 25 times what? dy. This dy, which is from 3 to 6. Okay, that's for the upper part of the pool. This 20, the width, which is 20, and the length, which is 25, is fixed. So the level of the water is changing. So depending on the differential volume that we are considering, but it will be starting from 3 to 6 because it's the upper part of the pool. So you have your 3 to 6. Now this 500 came from this 20 times 25. So the 500 together with the dy is your actually the volume. The volume of your water, and this is the density. So you have now the mass of the water, which is in this case translated to the force, and this one is the displacement. Now that displacement is 8 minus y. Now remember that you are to pump all of this water here up to 2 feet above the tank. So you have here 8. This is the total height from 0 here. So 8, and then you have minus y. So let's say, for example, the volume that you are referring is until here, and that's the y. Then it would be the distance or the displacement would be this remaining part here. So that would be 8 minus the y. So this is your displacement. Because from here to here is 8 already. So in any particular differential element that you have chosen, its distance from the bottom of the tank is y. So then the height that will be covered is 8 minus y, or the same thing with the displacement of that differential volume of water. This is now the volume of the, this is rather the work in pumping out this volume of water. the top part of the pool. Okay? But of course, we still need to determine the volume, or rather the work needed to pump out the water at this section of our pool. Now, the bottom region lies on the interval. So, the bottom region lies on the interval 0, 3. So, from 0y to 3. Whereas the one on top is 3 to 6. So, you can see here the limits of integration is 3 to 6. For our second integral, that should be 0 to 3. We need to compute the length of the differential element in this interval, y, or we need to express this length here in terms of, again, the y, because this length depends on the y, whatever that y may be. It's something that is not fixed. So we need to write an equation for that. Now, you could see in terms of the points, I like to write the cross-section in here separately. So this is our trapezoidal cross-section for the bottom of the pool. This point here has the coordinates 10, 0. It's now using x and y equal to 0. So x is 10, y is 0. For this part here, you have 15 and 3. So you have here, this one is 15 and 3. X is 15, your y is 3. Okay, so this is a cross-section that is given already. Nahatag na siya yan. So we just need to place in the correct coordinates. So this is now your set of coordinates where you need to write the equation of the line representing this varying length of the differential volume of element in this section. Now, how do we find again this, the equation y equal to mx plus b? So you need to have the m. And what is the m? You have these two sets of points. You have the 10, 0 and the 15, 3. So in terms of y, you can start with this one. You will have 3 minus 0. And since I start here for the y, I also start here for the x. 15 minus, I have here 10. So I have here 3 over 5. So that's the slope. So you have y equal to 3 over 5x. Now question, what is the b? So from this equation that we have, so I'll first write it here, y is equal to 3 over 5x plus b. I'll assign any of these coordinates that I have. So when y is equal to 0, so this is 0, you have 3/5, your x is equal to 10 plus b. And b, then I'll write it here, is equal to negative 3 over 5 times 10. That's the reason why you see this formula here. The equation of the line relating this varying length of the cross-section at the bottom of the pool is y equal to 3 over 5x minus, it's not plus because in our computation here it's negative. So you will have here minus. So this has also 3 over 5. And this is also 3 over 5. So we'll place a parenthesis here. And I'll just place it 10. That way, in both of these terms, you will have 3 over 5 being multiplied. Okay, so y is equal to 3 over 5 times the quantity x minus 10. However, class, if you notice, this equation is y. And we're looking for an equation for this x. This x is varying because in here, your x will be shorter than the x in here. We need an equation of x in terms of y because in the first place, our displacement for work is in terms of y. So from this equation, just get an equation for x in terms of y. How would you do that? You just transfer here. So you will have 5 over 3y is equal to x minus 10. Sa luhod mo na daw. 5 over 3y is equal to x minus 10. So x is equal to 5 over 3y plus 10. And where is that? This is the equation that we will be using. For this ever-changing length for your differential volume at this side, at this part of the cross-section of your pool only. So you have the x times the 20 times the thickness. So the length of the differential element is the difference of the x value. So you will have x starting with 0 to x equal to 5 over 3y plus 10, giving a length of x equal to 5 over 3y plus 10. This is your x. Then what would be the formula in finding the volume of this particular differential volume so that you can find the work in pumping out the water in this section here? Okay, before I go to the last slide, so this particular solution of the sample problem, do you have any questions so far in here? So we have already the x for the lower part. So we need to have the dy, and then of course we have the 20, which is the width. This is already the work in pumping water in this part of our pool. We need to find the work in here. So far, any questions? Okay, so there's none. I'll erase my markings and we'll proceed to the next. So again, the pool is 20 feet wide. I mentioned that already. This differential element represents a thin slice of water with volume. So the volume of the water is the width times the length times the thickness, which is dy. The height is the function. The height function rather is the same as before, which is 8 minus y. Because your differential volume class, your differential element would really be represented in terms of its location from the bottom of the pool as y. And since the pool all in all is, or in terms of the total distance in which your water is to be pumped out of the pool, it would be 8. So the displacement is 8 minus y. So you have here 8 minus y. This 62 is the density, this 20 is the width, and this is the length. The width and the length. And this is actually your x. Okay? I've shown it in the previous slide. And this one is the thickness to give you a volume. The width times the length times the thickness. That's the volume. Multiplied to the density, that would be the force. Now, this is your displacement, the 8 minus y. So notice that since our y represents the height of the water inside our irregularly shaped swimming pool, then we have the limit here, 0 to 3, because we're considering only the water at the bottom part of the pool. So 0 to 3. If you're going to process this one, your answer for the work done is 299,520 foot-pound force. Now, the total work done would be the work in pumping the fluid at the bottom and at the top of the swimming pool. So these are the two works. This would be the total work. Now, notice how the emptying of the bottom of the pool almost performs or requires the same work as that of emptying the top. Let me see. So this is the bottom and this is the top. There is lesser work here for the top, but greater work at the bottom part of that pool because there's greater displacement. So in terms of the displacement of the differential volume of water, it's bigger at the bottom of the pool. The top portion travels a shorter distance, but has more water. And in the end, the extra water produces more work. Okay? Now, any question as to this problem? Okay, no more questions here. Okay.